evening, depending on where you are. We're glad to have you with us today for a webinar having to do with the changes and things that have occurred in HD radio in the past few years. And I'm Chuck Kelly, Director of Sales for Nautel, and with me is Mike Woods, Head of Development for Nautel, and he's been very, very involved in all of the work here. You've probably seen some technical papers that he's written, and talked to him at NAB about the wizardry that is behind the engineering department here at Nautel and our HD radio products. Good afternoon, Mike.
So hello, everyone.
So we're going to talk about a number of things today. First, we're going to contrast 2014 to 2009. That's kind of arbitrary, but it's the last 5 years. What's changed? Because when you live it, you don't necessarily see the forest for the trees. And then secondly, we're going to do a very basic overview of how do you upgrade to HD radio. We're going to talk about why increase HD injection levels, why have HD power boost. We're going to talk about monitoring HD signal quality. And then the most fun part of the broadcast is always when we go live to a transmitter through the AUI and play some experiments, and I basically see if I can get Mike to blow up the transmitter. And then we'll take your questions. And that's a very important point, because on the tool that you have in GoToWebinar is an opportunity for you to ask questions. And we won't answer them right now, but we'll answer them at the very end of the webinar. So please do put your questions in there. So let's get started. What's changed in HD radio in the past 5 years? Well, the biggest change probably is that 35% of the new cars being sold today now have HD radios in the United States, and nearly 18 million HD radios have been sold so far. As a matter of fact, a new HD equipped car is sold every 4.5 seconds in the United States. The coverage issue, higher FM injection levels that have been approved by the Federal Communications Commission have improved digital coverage significantly, and we'll talk about why that is. And we're going to talk about how technology has improved. The transmitter systems from all suppliers are much more robust and simpler to configure. And in terms of actually making a buck from digital radio, monetization, new ways of using HD radio have been developed, including traffic and driving translators. We'll talk about that as well. And further, some stations with creative HD programming or even HD3 programming are actually showing in the ratings today, and that's really the proof in the pudding on digital radio. And we're also going to talk about implementation and user experience. There's not any technology that's ever been developed that didn't have a downside, and there are people that we respect, respected engineers that maintain that interference, which is caused by digital sidebands, is damaging both AM and FM coverage, and there are some concerns persisting relating to coverage. So we're going to try to talk about all of those things. As I mentioned, the technology has improved as well, and we at Nautel like to think that we had a part to play in making that change. And so Nautel has pioneered several technologies that have made significant improvements in the last 5 years. Reliable HD transport, which solves many issues related to IP STLs. It used to be that if you dropped a packet, your station was off the air for a while, and it isn't so if you use HD reliable transport. We introduced the first 40 kilowatt solid state FM transmitter, which made it possible to do high power stations without resorting to separate antennas or a high level combined with the attendant issues that related to both of those. We introduced a constellation view which shows HD carriers on the AUI. We introduced HD power boost. This was a huge thing. It's a patented PAPR technique, which stands to peak to average power ratio, which improves the digital power capability while improving the overall electrical efficiency. And we were the first to introduce asymmetrical sideband capability, and we introduced just this last NAB, we introduced detailed MER measurement built right into the transmitter, allowing measurement of specific sidebands. So we're going to talk about all these things, and a lot of them we'll show you as well. So what's changed on the HD radio front? Well, there's a lot more information available. Program information is available on the radios. A lot of stations are making great hay with the HD2 and HD3 channels, particularly in very niche formats. From a digital sound standpoint, it's now possible to do surround sound. The audio performance of HD radio is really very good. I don't know a lot of people that prefer the analog sound to digital radio. iTunes tagging, making it possible to actually market the content that you have on the station to the listeners. Artist experience, putting pictures on the screen of the radio or whatever you're listening on, and it allows you to see the album cover and that sort of thing. And traffic. Traffic is a very important thing. I'm not sure if people everywhere realize that in many stations in major markets, the highest rated format in the morning and the afternoon drive time is actually the traffic report. And so this allows you to listen to whatever music you want to listen to, yet get access to that important traffic information in a very visual way. And some of the organizations include the Broadcasters Traffic Consortium that are doing and helping facilitate this traffic technology for radio stations around the United States. So this is your radio station on a normal radio, pretty cool. This is your radio station on HD radio. So you've got a lot more of the bling, I guess you would say, that a listener would pick up on. Here's what's happened in receiver availability. As we said, you know, if you look at just what happens day to day today, you may not see it happening, but we're nearly 18 million receivers in the market, and nearly 7 million receivers were sold in the last year alone, from 2012 to 2013. So it's really a success story, I think, in terms of the number of receivers in the market. Battle for the Dash, there's 34 auto brands all currently offering factory-installed HD radio technology, virtually all the main brands. If you talk about how you go about upgrading to digital radio, there's three major decisions points, the choices you've got. You can do high-power hybrid. In this technology, both the analog and the digital signal are created within the same transmitter. And then there's space combined or antenna combined, where you have two separate antennas, one for the digital and one for the analog. And then you have high power combined, where we actually use a combiner. We're going to talk more about these and some changes in technology that have occurred as well, and the pluses and minuses of them later in the broadcast. These are the basics that you need. If you buy from Nautel, you need an Next-Gen card, you need an exporter. If you're going to do HD2, HD3, or HD4, you need an importer. And then you're going to need the audio processing for each of the channels as well. And, of course, you process the digital differently than you process the analog to take maximum advantage of the dynamic range and frequency response of the respective channels. So why an HD radio power increase? Well, it provides better inside reception. In the past, they've said that they needed the power increase because it improved the penetration of buildings, and I guess that is a little bit of a misunderstanding as far as I'm concerned. Analog signals penetrate a building just the same as a digital signal. Thank you very much. But in reality, where the problem is the attenuation that the building provides in conjunction with the higher noise floor inside. And noise is really the relevant issue. The increased noise floor from microprocessors and light dimmers and all the things that we have today causes the signals to be competing for. It's not, we're not losing signal, we're actually losing the ratio of desired signal to undesired signal. So the HD power increase provided additional coverage to 60 dBu contour and beyond, less blending and multicast, and better reception on portable radios. So here's what we were talking about, the kind of introduction in various technologies that started to add to the noise floor as seen by the radio stations around the United States. And there's another paper that we presented a few years ago that talked about the coverage area of many radio stations, both AM and FM, is actually being restricted by this noise floor. You know, over a period of maybe 10 or 20 years, could be as much as 30% decrease in the coverage area as a result of the increase in noise floor. They're still running 10 kilowatts or 50 kilowatts or whatever it is, but their coverage area is actually reduced because of the increased noise floor. Here's an example of what happened in Boston when they did digital trials and tried to figure out what the advantage would be. And you can see here, when you were running the 20 dB injection level, minus 20 dB relative to carrier, you could see the red areas here are areas that did not have good HD reception. When we went to minus 14, made a huge difference, and then -10, if you can go up that high, it makes even a larger difference yet. So now let's talk about noise. Here is the typical HD signal. You've got the analog FM, and you've got the two -20 dB subchannels or HD carriers, one on either side of the analog FM. And as the noise floor comes up, it's okay until it isn't okay. And now it's not okay, and you're still hearing the analog, maybe a bit noisy, but the digital is gone. And so the only thing you can do is pop up some additional subcarriers and raise that gain a bit. And now you've got closer to parity in the digital side than you had to the analog side. And the other interesting thing that happens, though, is that we don't live in a vacuum. There are other stations on the band in most parts of this country. And so if another station pops up, it could potentially have interference from this other sideband that's at -10. So that became an interesting question. What has happened is in some stations, they have found it's necessary to not have those sidebands be the same amplitude. So let's talk about how this happened. All stations were originally limited to an injection level of -20, as we discussed. In 2010, the FCC approved most stations to raise the digital injection to -14, and many stations could go up even higher to -10. Some stations, due to adjacent channel spacing, could only go to -14 on one side, but somewhat higher on the other. And a station operating with -10 on one sideband and -14 on the other has better coverage than -14, but not as good as -10, which is kind of what you'd expect. There's some complicated mathematics that can be played there, but that's basically what you need to know. So the FCC released a report and order, changed the rules to allow a 6 dB increase in the digital injection level to a -14 injection level for all stations except Super B and C. And beyond 60 dB up to maybe 10 dB, which is to a -10 dB injection level, a little confusing, subject to a formula developed by NPR Labs. And then they established procedures for remediating harmful interference in cases above -20, and the FCC reserves the right to revisit the issue if widespread interference results. And asymmetrical sidebands are possible by an STA application. Now, Mike, you ran into a situation where a station actually had some problems and was able to solve those issues because of asymmetrical sidebands.
Yeah, this is on the West Coast. And it was actually a U.S. station in Washington and a Canadian station in Vancouver. And the U.S. station turned on HD radio, or actually increased their sideband power level, and unfortunately caused interference. And through some conference calls and talking about capabilities of the NB transmitter, we went to an asymmetrical operating mode and were able to eliminate the interference. So both parties were very happy.
That was done cooperatively. The FCC really didn't have to get involved.
No, that's correct. Yeah,
that's really the best.
Our conference call, I think, had 14 people on it, but
fair enough.
All said and done, everybody was happy. So
excellent.
It's definitely a real world application.
So Nautel went ahead and introduced asymmetrical sidebands in 2010 and won a Cool Stuff award for it. And what it does is it allows you to optimize coverage to the actual interference conditions in your market. As you can see on this screen, that we are showing asymmetrical sidebands on this AUI screen. And this is what we were mentioning with regard to complaint remediation. Radio stations today want to be good neighbors, and so they don't want to create interference to adjacent channels. And so this is the methodology that the FCC is suggesting to remediate complaints. And just as Mike just said, voluntary reductions and mutual resolution between the parties is really key. That's the best thing that can happen. So there's a notification procedure when you go to -14, and if you want to go above that, one of the things that's key to note is that since in the past 5 years, we have introduced what we call the RF toolkit, and part of that RF toolkit is the NPR HD radio calculator. And you could write down this big long string here of an address to get to it. It's free, or you can go over here and take a shot of that QV code, and you can go to that. It's you can log in and figure out what capability your station would have given the FCC database in terms of your ability to go beyond -14. So of the different methods that exist to get increased coverage, suppose you've already invested in your HD radio transmitter and you want to increase the HD sideband injection level. One of the possibilities is to add a bay or two to your antenna, and then you can reduce the analog level, and thus what you've done is to keep the same ERP, the same effective radiated power, but actually reduce the ratio between the analog and the digital, and the net effect in the listening area is that you've got the same analog coverage, but your digital coverage has improved. And so that's one possibility. There are costs to that, including the space in the tower, the weight and the wind load, impedance matching, coverage and nulls, digital spectral purity, because there's a tighter requirement on the transmitter. On the other hand, our transmitters have some very, very good test equipment built in to make sure that you are providing the performance to the adjacent channels that you're obligated to do. Another possibility is to go to a higher power hybrid transmitter. It's a simple architecture, a 40 kilowatt transmitter, single box installation. Higher HD injection levels may reduce the analog TPO, and you may need to replace your transmitter depending on how much headroom you have in your transmitter with your current injection level. And in general, higher injection levels increase the PAPR, the peak to average power ratio, and thus it reduces the efficiency. On the flip side, HD power boost increases the digital injection level and efficiency of the existing transmitter. So it may be possible that you could actually get a significant increase just by turning on HD power boost. You may not actually have to change your transmitter. And another way to do it is HD power, high power combined, where you take a lower power HD transmitter, which is doing HD only, and a higher power analog transmitter, and combine them in a combiner, and then send that to the antenna. Unfortunately, with conventional technology, a very significant amount of the power ends up going 24/7 right into the dummy load. And that's not a very efficient system. Most people don't like that too much. One cool thing is that ERI, the antenna manufacturer, has come out with new combiner technology that represents itself as saying that they can reduce those losses significantly. And so that may be a very, very viable situation. And I know of a number of stations who have made the decision that they may buy an analog transmitter for their main transmitter today, like the MD Lite, and then in the future they may add another digital-only transmitter if they decide to go with HD and use exactly this method to get to digital radio. And then there's space combined, which we talked about, which is two antennas. The question is, do you have the tower and the building space? You've got to make absolutely sure that the analog and the digital radiation patterns are exactly the same. You've got to make sure that there is no intermodulational distortion between the analog and the digital. So the scenario here is potentially the analog transmitter may be sending out the signal it's supposed to send out. It's received in the digital antenna and it will transmitter, and now that causes intermodulational distortion, which is a problem. So you may need to have higher power filters and or circulators in that scenario. And you need to verify the digital antenna system ratings for voltage and power. And there's been technology improvements in the transmitters that help to facilitate this as well. And now a biggie, the HD power boost technology. Mike, would you like to kind of explain HD power boost and what it does? Give us the, this has been a 2-hour presentation I've heard Phil give in the past, and lovely pictures of rotating vectors and things, but give us the...
Yeah, the essence of it, HD radio is adding amplitude component. It's adding quadrature phase shift modulated sidebands to the signal. In the original analog FM signal, that was a constant amplitude signal. So now we're adding an amplitude component. So we now have, we hear this term a lot, PAPR, peak to average power ratio. So the signal, if you look at it in the time domain, would be changing its amplitude. This HD power boost is an algorithm that runs inside the FM exciter, and it looks at the digital signal, looks at the analog signal, and tries to combine them in such a way that it minimizes the peaks that occur.
Okay.
And at the end of the day, peaks are only, to be broadcasted need transistors. So we want to minimize those peaks, minimize the size of the transmitter, and hopefully minimize cost and maximize efficiency. So it's a peak reduction algorithm at the end of it, in its essence.
Okay. But how does it also improve the efficiency? Because that's kind of, it seems
yeah. So
counterintuitive.
this goes to the amplifier's operation. When an amplifier is running in a linear fashion, so that means you're biasing the gate or the base, you're always drawing some kind of quiescent current, and the signal that you're amplifying, the amplitude of that versus what the peak capability of the amplifier is, that ratio results in how good the efficiency is. So if we can utilize more of the transistor's available power, and HG radio reduces that peak, we can lower the DC voltage on the final stage amplifiers, and we can use that available power more, and it ends up the amplifiers themselves, still on linear fashion, are operating in a more efficient mode of operation.
So if we take this thing to extremes, if you had a transmitter that was designed for 40 kilowatts, and you only had tiny little peaks in it that would do 40 kilowatts for a microsecond, and the rest of the time was no power,
right,
you'd have a very inefficient transmitter.
That's
if, on the other hand, your 40 kilowatts of carrier down CW power, that's the most efficient it could be. And what this is doing is actually increasing the average level of the RF to closer to the maximum capability.
Right.
And that means that you get a higher efficiency. Okay, very good. That's a question a lot of people end up asking. Now, explain the constellation view for us.
So the digital sidebands, when they transmit their information, it's done through their phase. So again, if you looked in the time domain, I think most people are familiar with sine waves. So if the sine wave was to start at 0 degrees and rise, that would perhaps represent 2 bits of information, perhaps 0, 0. If the sine wave was starting maybe at its peak at 90 degrees and falling, that could be a different 2 bits. So if there's 4 possible phases of each of these carriers. When it's being received, how well is that phase information maintained through the transmitter and through the reception system?
Okay.
The constellation is representing the phase and amplitude of that received signal. And so if it was right in the center point on the I guess it would be the 1, 1.
In other words, if we envision dots here
Yeah.
and here and here and here, the closer to dots it would be,
the closer the dots,
the higher quality.
The ideal of the signal would be.
Yep.
And the essentially no digital distortion of that signal.
Okay, good. And one of the things that people ask us is, well, let's quantify the value of the efficiency improvement. And as you can see, it depends. You get more improvement and more savings the higher injection level you get. That's kind of, that makes sense.
Yeah, so the more HG radio signal that we're adding to our analog, the higher the peak to average ratio is, the more power boost has to work with.
But you can see here that the typical station at -14, which is where pretty much everybody is allowed, it can expect in a 40 kilowatt transmitter to see $5,200 savings per year at, I think it was 12 cents per kilowatt hour. And so this means that the return on investment of the purchase for the HD radio software, the purchase of the algorithm, is 2 years, which is a very fast ROI. So and it's even faster if you're using a higher injection level. One of the things that people are doing with these translators now is they're actually using translators in part to light up, to draw, or using HD radio to serve as an STL to drive a translator, and it's a very effective way of getting a high quality signal to a translator, potentially from an AM station or what have you. It's a very effective tool, and a lot of stations are now using this. The question you get into is, okay, you're a station that bought a transmitter 5 years ago or whatever, and how do you know if you're transmitting a high quality signal? How do you know what the quality of the signal is, the accuracy of the signal, the bandwidth of the signal, how much of a good neighbor you are to the adjacent channels? It's tough because the kind of measurement technology is very expensive and or not available in the industry today. And so what the figure of merit, certainly as developed by Ubiquity and HD Radio and other signals companies, is called MER. It's the modulation error ratio, and Mike alluded to it before. It's how tightly packed the constellation displays are, how more like a dot they are. It's based on a demodulated actual transmitted signal, and it looks at the amount of error present in that signal, and it's the ratio of the desired versus the undesired, kind of like signal-to-noise ratio. And it's an indication of resulting coverage reduction as well. So this is a this is a display of the actual coverage reduction in your service contour in your digital signal from having a higher or a lower MER number. So higher is better. And Mike, you were explaining, to put these things into perspective, the Ubiquity standard number.
Right. So the Ubiquity waveform has an inherent PAPR algorithm running on it, and that results in about a 17 dB MER.
So MER for the standard iBox signal will be right in this part, and a negligible effect on the contour. So tell me what happens with the various different, what's the standard Nautel without HD power boost?
Our standard MER is 23 dB.
Okay. So that's way up here and much, much better.
That's right. And when we're running full power boost, it is at 14.5.
Okay, which is at the recommended spot for Ubiquity. And,
Right.
and what you're doing is you're trading off. And we'll show this when we go to the transmitter and in the live demonstration. You trade off MER for increased power capability and increased efficiency.
Right.
Okay. So this is the point when we get to go over and switch and start showing the transmitter that's operating right now in our test room. And there it is.
So we have an NV5 operating in the engineering lab, 2.4 kilowatts, asymmetrical sidebands, -10 on the lower, -14 on the upper.
Okay.
And we've set up the operating point to clear the mask with very comfortable margin, and you can see the constellation. We're not running power boost, so the MER is
at the moment
on those carriers that we're looking at is close to 25 dB.
Well, let's look at that tool right now, and when we expand it, we get the capability of looking at the carriers and choosing which ones we want. The worst ones would be right towards the middle, I believe, in here.
Right. So we're looking at across the top there. Each one of these columns represents a subgroup of carriers, and they are displayed in the way they look in the RF spectrum.
Now, it's interesting, Mike. I was thinking to myself, why is it the ones on the left are different than the ones on the right? And then I realized, duh, it's because we're asymmetrical modulation.
Right.
Okay.
Yeah.
Very good. So
yeah, you can highlight any one of these with your mouse, or if you're at locally on the transmitter. Yeah, and then in the scroll table down to the right here, it'll tell you what subgroup you're looking at.
Yeah.
And whether it's the data carriers are quadrature phase shift king, so we can see all 4 points in the constellation.
Right.
And the reference, if you want to grab this one above it here, that would be binary. So there's only 2 points.
Okay. Very good. And one of the things that people use this for is if you begin to see a reduction towards the middle here that's substantial, it may mean that your SCA level is too high or your modulation level, you're overmodulating, and that's actually causing interference from analog to digital.
So the MER number that's being displayed is for that individual
which is
subgroup.
164 kilohertz away from the
correct,
carrier.
positive 164 from the center.
Right, and if I click on this one here, that's much closer, and the MER is just slightly less.
Right.
Okay, which is about what you'd expect, I guess.
And the amplitude of each one of these columns is telling you MER at a glance, so you can quickly tell which ones are.
And this one's less because we have less injection?
More injection.
Higher injection. That's it. Okay.
-10 on the lower.
Right. Okay.
So that would be reaching a peak possibly in the transmitter's amplifiers.
Now, another thing that's very important is the spectrum analyzer that's included in these transmitters. spectrum analyzer is showing that we are, gosh, more than 10 dB below.
Right. So this is another metric that we use in setting up the transmitter, and very, very important for adjacent channel interference.
Sure.
And the bandwidth shown here is usually the most important. These little bumps that are occurring on either side are what known as the intermodulation, third order intermodulation.
Right.
So you can see in blue, that's the mask that we have to meet.
That's the FCC
mask.
That's
the FCC/NRSC mask, yes.
Right. And you can see here the fact that we are running asymmetrical on sidebands. We're down 31 there, and we're down 35 here.
Right.
So.
And this isn't a 1 kilohertz resolution bandwidth, because that does affect the.
Sure.
The
okay.
display.
So let's play with it then. Let's come up to the menu here, and let's go to presets. And let's turn on HD Power Boost. Is that a reasonable thing to do?
Sure. So we can adjust many parameters. We can adjust the injection levels. We can inject, obviously, power, frequency, turn on Power Boost.
What voltage would you like to try?
Because we're reducing the peaks, because we're turning on Power Boost, we can lower that probably 3 volts from what it was.
So it was 45 before, so we'll go to 42.
Yeah.
And now we'll hit save. Now, it's going to take time before this all takes effect, and things will look a little dicey in the meantime, but that's because the transmitter is going through the process of doing adaptive pre-correction.
Correct.
And as you can see here, this is the lookup table with the analog to analog correction, and you can see it actually moving down as it makes minute
AM to AM correction, yes. So, so this is the amplitude component of the pre-correction, so we're actually reducing the high amplitude peaks, and we're doing the same with the low amplitude.
Now, we didn't mention it before. I didn't highlight it before, but we're actually looking at the DC to RF efficiency here, and it was in the 40-somethings before, and now it's 51, almost 52% PA efficiency. And you're still clearing the mask. If I open this up here, you're still clearing the mask by an impressive amount.
Right. So one of the main variables that we have to work with here is the PA voltage on the final stage amplifier. So we could lower that a little bit and gain efficiency. Our spectrum is going to degrade a little bit, but
so we do that one more time?
Yeah, we can drop that another maybe 1.5 volts. So 40.5.
Yep.
And we'll see so you get efficiency and you give up
a little bit of MER headroom. So you can choose depending on your environment too. So we will see, as now this is going through the readjustment process again, we'll see the efficiency change, we'll see the lookup table for the correction change again, and then we'll start to see the sidebands fall as it converges on the ideal equalization. The other interesting thing that's worth talking about, and it's important that people realize this, when you talk about the output power of the transmitter, Nautel always talks about the analog forward power because that's what your license talks about. And the digital forward power, we're talking about is a substantial amount, and the transmitter power is greater if you consider the digital forward power. Some people talk about the total forward power when they talk about the transmitter power, but that's not really what you want to communicate about. It's really the analog forward power, because that's what your license is designed around. So now you can see we're still passing the mask, although not by as much, but the DC to RF efficiency is up at 53.6%.
Right, so we've made an improvement there. We've given up a little bit on the mask. We're still passing by several dB.
Oh, yeah.
The shape of the correction curve has changed a little bit. And the other thing we didn't point out, when we turned on Power Boost, the MER has dropped.
Which is not surprising, because what's happening is the Power Boost algorithm is making considered changes in the waveform in order to maximize
it's
the
doing
peak to average
tiny
coverage.
manipulations of the amplitude and the phase of the digital carriers to stop peaks from occurring
at the same time.
And
all adding up into the most positive of numbers. Okay, good. What else would you like to show us on here, Mike?
Down the right-hand side, we've selected a 6 meters there that's user adjustable and savable now. As you mentioned, you can call out the individual powers for analog, digital.
There's hundreds of measurements we could have brought up. We just brought the ones up that seemed appropriate.
Another parameter that we use when optimizing power capability, we now have a meter for average PA dissipation. So this looks at the DC power in, the RF power out, figures out how much watts are in each FET.
And you would imagine, and it's true, that the DC or the PA dissipation has declined when the efficiency went up.
Yes, exactly.
So that's.
You should also note that the modulation that's being used here, we're running. The exciter has the ability to generate modulation inside its own DSP. So we're running left and right stereo with white noise on both channels. Okay. Just for demonstration purposes.
Sure. Okay. So let's go back and get to questions here in a second. See if I can do this properly. Yep. So just to recap a little bit, the NV series is our digital product, and it will take you from 3.5 kilowatts to 88 kilowatts of analog nameplate power, and it'll do upwards of 60 kilowatts at -14 in the 80 kilowatt version, and 42 kilowatts at -10 in the 80 kilowatt version. So the transmitter with power boost can be a very, very effective tool for you. The key things that we want to talk about in terms of the NV series innovations are high power with no tuning, no tubes, of course. Nautel has never produced a transmitter with a tube in 45 years, I might add. More redundancy, less downtime, advanced instrumentation and control, lower turnaround loss, reduced IMD, 100% remote access. And since we started just a few years ago with the NV series, 1,250 NV series transmitters have been shipped to date. Summary overall, 18 million HD radio receivers are now in the market. HD2 channels are now in the ratings. There are many compelling reasons apart from improved audio quality to take another look at HD radio, including feeding translators, mobile traffic, other data services. Nautel has led the industry with digital radio innovation, including HD power boost, 40 kilowatt solid state transmitter, HD reliable transport, asymmetrical sidebands at no extra cost, MER measurement at no extra cost, and we're not done yet. For those of you who are coming to NAB, there are some exciting things to show you there, and we're delighted about it. So we promised we would get to questions, and now it's time to get to them. There's an easy question first, one I can even answer. Craig asks, what's the AUI stand for? It stands for Advanced User Interface, and the reason we call it an AUI, it's not just a marketingism, is that the real value of the AUI is the fact that it's monitoring so many things so deep in the transmitter. It's monitoring every fan RPM, every voltage, every current, every temperature. It's much more than a remote control system, and it's much more than a GUI. Are automobiles with HD radios available in Canada? Not yet, although HD radio is going through a transition here in Canada, and it may very well be adopted. It is actually legal to broadcast in Nautel. We have a little transmitter here in Halifax where we actually put HD radio on the air, but it's special temporary authority. But it does make sense. The Canadian market has the potential to draw upon the same market of receivers that are built and sold in the U.S. So they come from a common pool, and so it would make sense for the receivers to be available up here in time. Is there any hope for improvement in the audio quality? There's a lot of anomalies in HD Classical that is very irritating. Good question. I know that there are friends of mine who have extremely good ears, and they hear things that they don't like. I don't know the answer. I think that the only thing that you can possibly do at the moment is to dedicate 100% of the bandwidth that is available within HD to the codecs, and so don't have any secondary channels if you really want it's obviously a trade-off. If you want the best audio quality, you don't subdivide your bandwidth and have multiple signals. Thank you for that comment. Are there any AM HD table radios? Yeah, I have one, and I know of several more. They are in short supply. I would say right now that HD FM is doing much better than HD AM, but I do know of new crops of receivers that are coming out that will again support AM. So that's a good point. And there's a gentleman that disagrees about the situation in Vancouver. The U.S. he says, I believe returned to minus 14 dB to carrier and is still causing serious interference. So that's
that's interesting
an update.
Point. Okay.
Update.
When I left it, it had been solved, and it was solved through asymmetrical. So I'd be interested in hearing more.
Want some copies about some of the slides? That this whole webinar will be available online. And there's a station, and there's another update from another listener here that is saying that in fact CJSA is actually broadcasting right now with HD radio in Canada. So there's an increase in interest in IBOC in Canada. And there's questions about the V10 and how it can be modified to transmit. And you can talk to our customer service department about how that can be done.
So just quickly, the V10 is HD compatible.
Yep. Running digital sidebands, how do you treat your analog modulation? Is it 100%, or do you consider the digital as an STA and increase modulation to 105% or 110%, or is that counterproductive as the analog carrier can splatter into the digital sidebands? Thank you for that, Dan. It's actually completely different. It's measured completely different. Your analog modulation is completely separately measured than your digital modulation. They're not even considered in the same breath.
Yeah, the splatter is perhaps something that happens in receivers, but it's not part of the measurement technique.
Yep. It says especially when running an HD4. Oh, that's that's a continuation. He's asking about.
Yes.
Yeah.
Yeah, so HD4 typically results in more HD carriers, and they end up getting closer to the analog channel, the analog space on the RF spectrum.
Another really excellent, nothing like the listeners keeping us honest here. A listener has said, well, what about the VS series? You're spending all this time talking about the NV series. Everything we've said here is also true with the VS if you have the VSHD adapter.
Yes, so the VS transmitter requires a second unit called VSHD to operate in HD mode, and it effectively is using the same exciter, same DSPs as the NV, so everything we've talked about here applies to it.
Yep. And there's another person here asking a very pertinent question, a very timely question, and that is the HD viable and practical for LPFM? From a technical standpoint, yeah, sure, we can do that today. The the VSHD also adapts to the HD radio LPFM transmitter, and it's type accepted in the whole 9 yards, so all is good on that front. Whether or not the one-time capital costs of all the HD equipment make sense in the business model of an LPFM station, I can't answer that question. That's too specific. But I thank you for asking. I have a 2-year-old NV7.5 that's stripped out the HD components to keep the cost down. Now that I'm really ready to go with HD, what components are needed? Will I need a new exciter or any new exporter-importer products coming out to market that I should know about? Will there be a lower cost option?
So the two essential components you need are XGen and exporter. So the exporter takes the audio.
Exporter Plus in this case.
Exporter Plus is the latest version.
Yep.
Exporter Plus takes the digital audio and then converts that to an Ethernet signal, and XGen takes that Ethernet signal and converts it to an RF signal.
So, Joe, the good news is, thank you for your question, Joe.
And
the good news is, yes, we can do that. And your exciter, your transmitter is all perfectly compatible with digital radio, and you're all ready to go.
HD Power Boost was something that came along a couple years into the life of the NV product. But
depending on when you bought it, it may be that you'll need to replace the exciter as well. But that's not necessarily true if you don't need HD Power Boost.
Correct. Yeah.
Okay. Any pre-information for Generation 4 HD? No, I don't have anything I can report on that right now, but thank you, Dan. Can you start out with symmetrical sidebands and then update to asymmetrical sidebands? If so, what costs are involved with doing that? About 2 minutes.
Yeah.
And no cost.
No cost. So we can do that on the fly.
As we just
on a running transmitter, just as we demonstrated.
It says, are your statistics just for the U.S. or only the U.S. and Canada? And the answer is it's just for the U.S. We haven't considered candidate in the equation. We currently have a 6.6 kilowatt PEP. The analog, sounds like a ham there. The analog transmitter is 82.5% efficiency. We run RDS in addition to our analog program. What kind of AC power consumption increase would we tend to see? I would say you're probably looking at least 50% increase.
Depends on the operating conditions of the HD
and
signal.
Most importantly,
a lot
the
of
injection
variables.
level.
Yeah,
Yep.
Injection level, MP mode.
That's right.
They all affect efficiency.
Absolutely.
But if you send us the particulars, we could give you a pretty close number.
Okay. And what can be said about AM HD? What is the future like for AM HD radio? Good question. I think the future may boil down to what's going on right as we speak with people doing tests on the all-digital analog signal, which is, if you look at it, very close to DRM. It's very similar in that it uses a narrower channel, and it is not encumbered with trying to pass simultaneously the analog and the digital. But that's going to take a lot of receivers to be in the market, and that's why the hybrid system is in transition.
We are presenting a paper on that very subject.
And some work that we've done.
At the NAB this year, so
that's right.
If you get a chance to attend, that'd be great.
And with regard to transmitters, what is your idea on the process to transmit holographic images? Wow. I think I need to go out and have a drink before I think about that one. Thank you for that one. It's a good for a smile. Anyway, I think we've reached the end of the time that we have available. Any other questions we haven't had a chance to answer, we will answer offline by email. This is where you can find more information from the Nautel Waves newsletter, from our webinars. Important for you to know, if you found value in this webinar, it is available within a day or so. It'll be online in this subdirectory on nautel.com/webinars, and you can watch it at any time. We archive it. Also, check out our YouTube channel, our Nautel store, our Twitter, our everything we've got these days, our Facebook page. I almost forgot our Facebook page. Heaven forbid I forget our Facebook page. So I want to thank everybody for being a part of this webinar today. Thank you for asking all the excellent questions, keeping us honest. And it is our 45th year this month, so happy birthday to us. And thank you all for being with us. For Mike Woods, I'm Chuck Kelly, thanking you all very much.